Sagi is also from NREL, National Renewable Energy Lab, and Gretchen is from NIST. So great.
Assuming I heard the room was blank, so hopefully you guys can hear. Okay, so thanks for coming to our talk. Really, really appreciate it. This talk is essentially talking about the knowledge graphs for the research labs of the future. I'm Zisman, a researcher of computational science at the National Renewable Energy Laboratory. I have my collaborator, Gretchen Greene from the National Institute of Standards and Technology, NIST, and she's the Director of Research, Data, and Compute. A couple of contributors to this set of slides are Robert White, who's not here with us today. He's a senior data scientist at NREL, and Ambrish Nag, who's sitting here. He's also a senior data scientist. Okay. So, what is going to be the agenda? I think we probably prepared too many slides, so it's going to go pretty quickly. And then if we skip a lot of details, please come and talk to us afterwards. So, we'll give a quick introduction to NREL and NIST. We'll talk about how work is done at the lab, which is very important to put things into context. We'll talk about a couple of knowledge graph use cases, the vision for the research labs of the future, reimagining how organizations can do work at research institutions, looking forward, and a call for collaboration. It's going to be very important. So what do we do at NREL? So like I said, NREL is the National Renewable Energy Lab. We focus on renewable energy and energy efficiency. So those are the two big aspects. Everything from kind of the nanoscale quantum physics to large scale national level analysis of grid integration and energy and market analysis. So it kind of spans a wide breadth. Some of the sub areas are material science, chemistry, nanotechnology, resource data, including solar, wind, bio, geothermal, water, including waves and currents, renewable energy grid integration, energy efficiency. We do a lot of different things, including a lot of increasingly cross-collaborative work. You were part of the last presentation. It's kind of showing some of the connections between the work that gets done at NREL. Things like geospatial sciences, computational sciences, our center, and then data and software engineering. So putting things in context, and I think this is going to lead us to where knowledge graphs can come in and help. So what works is that we have domain experts that are world-class. It's a national lab, so we have that. That's all good. We have top-notch facilities, including supercomputing facilities, HPC, wet labs for chemistry, experimentation, and material science, experimental field work for testing PV modules, wind turbines, etc. Autonomy and creativity is encouraged. Our research is highly impactful. And what's kind of cool about NREL specifically, maybe it's a little different from what you would imagine of a federally funded laboratory, is that new technology is readily adopted in our work environment, like large language models. But some of the challenges that we face are ad hoc projects that can lead to duplicative efforts, difficulties in finding data and code, and integration. I think if you work at a research institution, it's very familiar to you. We have inconsistent software engineering processes. People and researchers have the freedom to do what they want. That creates a lot of difficulty for cross-domain collaboration. Knowledge transfer across domains. And then assets can become obsolete, so there's a lot of discovery of the wheel, so to speak. So those are some of the challenges. Let me pass it over to Gretchen right now.
Okay. So yeah, we have the tag team here. Thank you all for coming to this session. So we're partnering together, NREL and NIST. We have very similar backgrounds or institutional goals with large, complex research environments. So NIST, for those that don't know, is the only national metrology institute in the US. So it's a federal bureau under Department of Commerce, and it was created in 1901. So very, if you read any recent Washington Post reports, they are true. Our buildings are very old and in not in the best of shape. But anyway, we're happy to be here in this lovely facility here in this new tech center. Lots of different multidisciplinary areas of science, very cross-cutting work, laboratory science, wet labs, very fundamental, of course, standards. So if you think about AI, the standards for trustworthy AI, cybersecurity, but also a lot of domain expertise. So anything from forensics, materials science, which is where we were connected originally at NREL, disaster. I can't even name all the different domains, but a big focus now is on emerging technology. Okay, AI, of course, and also chips R&D, and you'll see a little bit about that in my talks. So NIST is broken up into several major laboratories. Some places call them institutes. Here's just a sampling of the various labs. And my effort now is cross-cutting with data and knowledge space. So here's just kind of a flavor of what we're grappling with. Again, this is like your iceberg, and with this very, very rich research data is very complex. It's really hard trying to take all the different contexts of research data and put them into knowledge structures. You can't rely just on text mining and conventional. There's just so many different sources of information. And those of us that have worked in this environment for a lot of years thought we would try to do something. Everybody loves Wikipedia. And we were like, wouldn't it be great at NIST if we can kind of pull and link all of our information together and start contextualizing it and using some of these cutting edge technologies for linked data. And so we started just at the very basics trying to create schematic structure. So here's one that was published recently for electron microscopy. That's a very, very important field in research in nano and many, many areas. And then we went forward with that to say, okay, we've got this like structure, but we've got these very complex laboratory environments. So we wanted to make this as, streamlined as possible to start automating ingest of data into storage, structuring it using schematic structures, and figuring out how to engineer all this. And we did it. We built this system called Nexus LLMs and rely on a lot of, tools that you hear about today with Amazon. But really, once you start doing this for one lab, then everybody's like, I want to do this too. So we then started broadening, and the community, like the community here today, really loves this community knowledge capabilities. And this is a huge area of growth in research today. And largely thanks to a lot of machine learning capabilities, data lakes and data mesh and things of that nature. So we've got the laboratory end of things, but we also have a lot of existing curated data. So at NIST, we also, on both ends in parallel, started building out this digital knowledge network. And it's kind of driving the two environments, the laboratory automated generating data with this discovery environment. And so you could explore data.nis.gov. And some of us come from a background in data, so we really wanted to promote open source, standards-driven architecture and partnering. I was very involved, I still am, with the Research Data Alliance. I encourage all of you to get involved with them if you're interested in this. And there's also a federal data strategy for the US that we're heavily involved in. And so we took this to the next step, and we decided, we not only have information sources coming in from laboratory data sets, but we've got patent data, we've got various flavors, and we've got expertise. A lot of what people want to know is where do I go, and who do I talk to? And so we started pulling all this together in like a scientific gateway. We're pulling together a lot of different distributed sources together and merging them into knowledge graphs. And people might go in looking for particular data sets, but then find patents or code resources as well. And really, we're looking at more than data. We're trying to take data and transform that into information and then get those deeper insights and knowledge for industry. And we also partner here. I want to give credit to Johns Hopkins University. They're helping us build out some of these capabilities for the new domain of manufacturing. And the CHIPS and Science Act, which is a really major new thrust in the US, we're involved in that, building out digital twins. And I think this is my last slide, but we are starting to explore, and just before we even embarking on collecting all the data, just trying to use this technology of knowledge graphs. We could start looking at basic data sets that we have in semiconductors and then discover all this other interrelated knowledge. So we're really excited about this technology and moving forward with it. And I think I'm ready to shift this back over to Sagi.
Awesome, thanks, Gretchen. Okay, cool. So I think we heard a little bit about some of the potential use cases and some of the actual use cases at NIST. And I kind of want to now move towards a forward-looking approach. So here's a kind of another really interesting use case, which I think is in its nascent stages. So laboratory automation. Okay, so before we get into what that could look like, I just wanted to present a quick slide about the material science or the material scientific cycle. It's really the scientific method in a way, but maybe a little bit more geared towards material sciences. So kind of starting up here, we have institutional knowledge that researchers at the labs may have. They may get some insights from previous theory and modeling, and then they're going to come up with a conjecture, potentially fabricate some sort of material structure, process it, and then there are a couple of different variables that could be used in processing and parameters for tuning experiments. You will make measurements, quality measurements. I'll show you some of that in the next slide. Analysis, so how do you analyze the data that you collect, interpret the data, learn, and then of course report it out, share your knowledge in publications, presentations, etc. And then that will be fed back into institutional knowledge, and then along with extra outside knowledge, you can complete the cycle. So we really think that the knowledge graph, of course, is going to sit somewhere over here. Okay, so here is an example of kind of the first experimental dabble of NREL in autonomous experimentation. So there's a paper here by D. Feba et al. And it's really an autonomous sputter synthesis thin film nitride. So it's really kind of a closed system that optimizes the deposition of titanium and silicon substrate, and it's doing so using Bayesian optimization. Now this is a kind of a closed system. The parameters for the system can be defined by domain expert, code written to do the optimization. But of course, this is just a closed system. So what's missing? Of course, there's kind of the actuation of the experiment. You need actuators to deal with samples. But then from a knowledge perspective, taking knowledge from one run to the next, from literature and other experiments, and helping design the next set of experiments. This is kind of missing in this type of picture. So we're hoping to take inspiration from a very recent paper that came out. It's a knowledge graph enabled digital twin framework by et al. And it's called a dynamic knowledge graph approach to distributed self-driven laboratories, which was published actually, I think, in February in Nature Communications. Basically what they did is they took two laboratories, one at the University of Cambridge, one in Singapore, and they essentially created a Pareto front for optimizing yield and cost of fabrication of chemical reactions. So they basically have knowledge graphs that are the digital twin kind of brain. And on top of the knowledge graph are multi-agent kind of these microservices that can do design of experiments, that can reason about chemical ontologies. And then they can actuate the hardware to actually do the experiments. So taking this as inspiration, if you take this kind of closed system that we have at NREL and putting it in context of the material science cycle, you'll essentially take a fabricated material and then make measurements like X-ray diffraction, transmission, reflection. Some of the details here are not that important, but the idea is that you're going to have a design of experiments engine that sits here in the middle. Is driven by artificial intelligence, digital twin framework, and then a knowledge graph on top of it to coordinate the semantics that actually going through this whole cycle. It's very complicated. You have domain knowledge, and then you also have actuation of instrumentation and equipment in the laboratory. Okay, so what is the dream? The dream is creating a metal organic chemical vapor deposition chamber for 3-5 solar cell materials. Lots of different variables here that would have to be optimized and tuned. And so building a knowledge graph enabled autonomous system, something like this, would really improve research productivity and output. So what are some of the impacts associated with that? Exploring material combinations efficiently, you'll have less waste. You can model using a digital twin the safety envelope system. If you tune different parameters, does that get you to some regimes that make the experimental setup less safe? And experimental throughput should increase, could be on the orders of 1-2 orders of magnitude. And then reduction in human error. Of course, that's the other benefit of automation. So for the laboratory of the future vision, so this is kind of how we see it. So we have researchers here in the middle, and there's domain science at the bottom, where you can ask domain relevant questions like where to place a wind turbine. That's a very common question that NREL can help answer. How do we integrate it into the grid? So that's domain science. Here is doing science. So everything that has to do with data, metadata stores, code repos, compute resources, a lot of different protocols, laboratory equipment. And a researcher has to kind of go in between these two different worlds and understand the two different worlds. And in the future, the aim is to have AI research assistants that can traverse these two separate universes. So here is kind of a robot that would replace, it's not going to replace the human, augment the human. We're not going to replace scientists anytime soon. But the question is, what is this robot going to actually do? So here's kind of the flavor of the week. If you go out and ask someone on the street how they would architect this type of system, they'll of course say, well, just use an LLM and create APIs to everything. So everything on the doing science part, well, we have APIs to code repos, data stores, compute, blah, 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 blah. And just maybe use like the LangChain agent methodology and let the robot come up with an action plan to do this kind of reasoning and planning on top of it. And then we could also feed using some RAG approach, unstructured multimodal data. But the question is, will this work? I think we heard, and if you've been to some of the talks yesterday and the day before, you'll see that not so fast. So of course, I found these two papers pretty interesting. There's one that came out by Microsoft, Sparks of Artificial General Intelligence, Early Experiments with GPT-4. And here's a quote: given the breadth and depth of GPT-4's capabilities, we believe that it could reasonably be viewed as an early and still incomplete version of an AGI system. Okay, pretty big claims. And there's another paper that came out, and they're both really accessible. I highly recommend reading it. It's called GPT-4 Can't Reason. And quote from this one, based on this analysis, the paper concludes that despite occasional flashes of analytical brilliance, GPT-4 is utterly incapable of reasoning. So what are we going to do with this? I think this is, I guess, the big question of this conference. So we're going to be a little bit more cautious and probably take the best of both worlds. So LLMs to interface with our knowledge graph-based digital twin. And then the reasoning engine is going to be some sort of neurosymbolic approach of large language models, graph neural nets. Okay, so these are maybe both on the deep learning side, plus a symbolic approach, and that will do the planning and then connect the APIs to everything. So this is what we're hoping to do. Of course, there are a lot of open questions still as part of this. But I think to really get AI assistants working, you have to think about the connective tissue between doing science and the domain science. I think the disconnected tissue between weight classes of a wind turbine and software modules that actually actuate the analysis, this is kind of where the magic is going to happen. So I'm not going to get into too much details here. A lot of work in integrating and bringing up as first-class citizens different types of people inside the organization and integration of different assets. These are major challenges for modern research labs. So if anyone has any experience with this or wants to talk about it, please, I'm open. And then, of course, a data mesh-based data ingestion. I'm kind of calling this the data knowledge infrastructure. So you have data on one side, the data mesh. This is a project that we're starting at NREL. It's a project called Data Share to integrate these distributed data sources, and then a bunch of applications here. So, Gretchen.
Oh, yeah.
We're almost done.
Yeah, thanks. So when you see the materials genome, it's not genetic engineering. This was way back in the day that this was a project that came out, the MGI, that was saying, hey, we can accelerate discovery of new materials for commercial applications. And there was a couple papers here written by Pusey as well as Stock that are showing we do expect there's going to be a progression with incorporating a lot of these techniques that Sagi was showing, that we will have more and more capabilities for having automation with laboratory research. And so there's actually some real projections here that are showing like by 2040, we should be able to have like very highly accessible things. And definitely the knowledge graphs are playing a part of this equation. And, you know, kind of reiterating some of the points Sagi was mentioning, that how we pull these different capabilities with digital technologies together with researchers and commercial spaces. A lot of the really interesting, there is a big convergence right now between science and these technologies that didn't exist before. So it's a really exciting time for people to get involved in these capabilities.
Awesome, thanks, Gretchen. Okay, so looking forward, some opportunities and some challenges. Opportunities is, I think, we're kind of at the precipice of how we can actually do science. And this goes to domain, on the domain side, and tools to help us sort through large hypotheses, spaces for experimentation, but then also an actuation of experiments, like I was telling you guys about the University of Cambridge paper, where they had a distributed laboratory setup. So transforming how we do science, we're kind of at this precipice. Increasing research productivity by orders of magnitude, of course, that's the holy grail. Source of truth for automated systems. This is perhaps kind of the biggest thing that knowledge graphs can do for these systems. You have to get things right. You cannot have hallucinations when you have an experimental setup in a wet laboratory. That's not gonna fly. New science can be done across the organizations, federations. I think we see different organizations. NASA over here was talking about their knowledge graph yesterday, NIST, NREL. There's a lot of opportunity here to pool and combine forces. Tackling challenges though, we have to reimagine organizational connectivity. I think a lot of people have experience with this here, and we haven't been able to solve this problem, but really lifting up operations and research on a level playing field. That's what knowledge graphs are really going to do for us, is by adding this connective tissue, doing science, the domain science. Those two, the connectivity of those two pieces will require cohesion across the organization, research and operational stuff. Knowledge infrastructure investments, showing the data mesh, the data share projects that NREL started, and then federation, infrastructure costs, knowledge laboratories, Triton stuff here. They're working on OKN project, which will combine different knowledge graphs and different domains together. These are the types of knowledge investments that are planned. Open columns and knowledge representations, LLMs, there's knowledge foundation, lots of open functions there. And of course, there's trust. Haven't heard too much about that at the conference so far, but of course, in this case, it's going to be something that's very, very important, and we need to start having conversations about it right now, especially when we're talking about human augmented agents for experimentation. So here's kind of our call for collaboration. We're currently identifying open research questions on how to achieve a lot of features of the call to join us. Thank you.
Thanks for the presentation. Very interesting.